Welcome all my dear student of FYBSc physics class. In previous lecture we studied the construction and working of diesel engine, but due to lack of times we can't completed it. So in this lecture we are going to see some parts, that is remaining part of the working of diesel engine. In previous lecture we studied two stroke. First stroke is charging stroke, and which is represented by the line A0A on this diesel cycle, and then charging stroke. Then we also study the compression stroke, which is represented by the curve AB on this diesel cycle. Now in this lecture we are going to see the remaining two strokes, that is working stroke and exhaust stroke. As we studied that the first operation is nothing but charging stroke, or charging stroke is nothing but the first operation of diesel cycle. As there are 4 strokes in the diesel cycle, but one cycle involves 6 operations like this: 1, 2, 3, 4, 5 and 6. We already discussed about the operation number 1 and 2, that is charging stroke and compression stroke. Now working stroke, in working stroke 3 operations are involved, and these operations are nothing but this and this. Okay. During working stroke, what happens during working stroke? The oil inlet valve I2 opens. We already studied that at the end of compression stroke the temperature is rises about 1000 degrees Celsius, because as compared to auto engine the compression ratio of diesel engine is large. In auto engine air is compressed or charged or mixture of 98% air and 2% petrol vapor are compressed up to 1/8 of its original volume, and in diesel cycle this air is compressed up to 1/70 of its original volume. That's why due to this large compression ratio, at the end of charging stroke the temperature is rises to about 1000 degrees Celsius. Okay. Now when third stroke is start, that is working stroke is start, at the beginning the outlet valve get opens, oil in the form of fine spray is forced into the cylinder under pressure. The temperature of the compressed air is above the ignition temperature. Okay, what I say, the temperature of the compressed air, that is 1000 degrees Celsius, is above the ignition temperature. The injected oil bursts immediately. Due to this the injected oil bursts quickly. An amount of heat, say Q1, here Q1 is produced. The supply of oil is regulated in such a way that during combustion the piston moves outward at constant pressure. The volume as well as temperature, both goes on increasing, but the change in volume is and change in temperature is also isobarically, or in another word we can say that the volume as well as temperature changes isobarically. Means what? There is a change in volume as well as there is a change in temperature, but these changes takes place takes place at constant pressure. Okay. Let volume increase from VB to VC, and temperature is also increased from TB to TC. This type of change, that is operation number 3, is represented by the line BC. Okay. Now, during the fourth operation, that is second part of working stroke, volume when the temperature has reached maximum value, that is, here we can say that temperature is rises to about 2000 degree Kelvin. The wall I2 closed when the temperature is rises to about 2000 degree Kelvin, then the inlet wall I2 is closed and supply of oil is cut off. When supply of oil is cut off, the high pressure of expanding hot gases pushes the piston outwards. That is, gas expands adiabatically. When gas expands adiabatically, obviously external work is done by the gas during expansion. And during this process, let volume is increased from VC to VD. But as the change is adiabatic, obviously there is a fall in pressure. Pressure is falls from PC to PD. Also, there is a fall in temperature due to adiabatic expansion, and this change in temperature is nothing but temperature falls from TC to TD. Okay, and the change of state, that is operation number 4, is represented by the curve CD. Now the last operation, 5th of the working stroke. During this operation, the outlet wall I3, that is exhaust wall, opens, and when I3 is opens, a part of hot gases along with an amount of heat, say Q2, goes out. The pressure and temperature of the gas obviously suddenly falls. The pressure falls from PD to PA, and temperature is also from TD to TA. That is what the pressure and temperature of the gas obviously suddenly decreases. The change takes place at constant volume. The change takes place at constant volume. Let pressure and temperature of the gas decreases from PD to PA and temperature TD to TA respectively. The change of state, that is operation number 5, is shown by the line DA. In this way, working stroke is completed. Now the last stroke, that is exhaust stroke. During exhaust stroke, the piston moves inwards. The wall I3 is already open and piston moves inwards, and when piston moves inwards, the remaining part of the hot gases, that is mixture of burnt and unburnt gases, is forced out. The change in volume of the gas occurs isobarically, that is A to A0. Okay. The change of state, that is operation number 6, is represented by the line A0. In this way, the original state is restored, and when original state is restored, the cycle completes. Okay. In this way, this is a very simple working of diesel cycle, diesel engine, which is understand with the help of this diesel cycle. Now we are going to calculate, or we are going to obtain an expression for work done. we can obtain an expression for efficiency of diesel engine. This point is also very important for exam point of view. Now, efficiency of diesel engine. Efficiency of diesel engine. The expression for efficiency of diesel engine is based on two assumptions like auto engine and auto cycle. Efficiency of auto engine and efficiency of. Okay. Which are these assumptions? Make your concentration. The expression for efficiency of the engine, that is diesel engine, is based on two assumptions. First assumption is that at every stage, this or this or this, at every stage, the change is reversible. And the second assumption is very important. The mixture of air and oil behaves like a perfect gas. Okay, or in a simple word we can say that the behavior of the mixture should be like or should behave like a perfect gas. Okay. Now, in this figure of diesel cycle, the two process, that is A0A and A0A and A0 are getting cancelled with each other. Okay. And hence, a remaining part, we have only remaining part is like this, and this is nothing but the figure for calculating the efficiency of diesel engine. In this figure, the line BC, during this operation BC, the heat Q1 is produced, or we can say that heat Q1 is produced during isobaric change BC, and heat Q2 is transferred to the surrounding along line dA. Okay. See here, the amount of heat absorbed at constant pressure Q1 is equal to mCp Tc minus Tb. Suppose this is expression 1. This is the amount of heat absorbed or produced at constant pressure along BC, and heat Q2 is rejected or transferred to the surrounding at constant volume, that is isochoric change from D to A. So, Q2 is equal to mCv in bracket Td minus Ta. Suppose this is expression 2. Okay. But we have the formula for efficiency is nothing but eta is equal to Q1 minus Q2 upon Q1, where Q1 minus Q2 is the net change in heat, net amount of change in heat, and Q1 is the supplied energy. Okay. Or from this equation we can write 1 minus Q2 upon Q1. Okay. Now, suppose this is equation 3, or instead of this we can put the value of Q1 and Q2. We have eta is equal to 1 minus mCp Td minus Tc, this one, upon m CV, sorry, CV, and here Cp Tc minus Tb. M is getting cancelled with this m, and instead of this we can write eta is equal to 1 minus 1 upon Cp by Cv into Td minus Tc upon Tc minus Tb. Okay, sorry, Td minus Ta. Td minus Ta. Now, but we know that Cp upon Cv is gamma, which is the ratio of two specific heats. Therefore, eta is equal to 1 minus 1 upon gamma into Td minus Ta upon Tc minus Tb, and this is equation 3. Okay. Now, in order to solve this equation, moreover, or further, in order to solve this equation further, we have to consider that point C and D lie on the same adiabatic. Therefore, we have to calculate, or we have to obtain the adiabatic relation between temperature and the volume with these two respective points, that is C and D. Therefore, Tc Vd, sorry, Tc Vc raised to gamma minus 1. This is the adiabatic relation between temperature and volume at point C, and Td Vd raised to gamma minus 1 is the adiabatic relation at point, adiabatic relation between temperature and volume at point D. Okay. As these 2 points are lies on the same adiabatic curve CD, we have Tc Vc raised to gamma minus 1 is equal to Td Vd raised to gamma minus 1. Okay. From this equation we can write Td is equal to Vc upon Vd raised to gamma minus 1 into Tc. Okay. But Vc upon Vd is the expansion ratio. Vc upon Vd is the expansion ratio. Okay. Therefore, we have Td is equal to 1 upon rho E raised to gamma minus 1 into Tc. Okay. Similarly, the point A and B lie on the same adiabatic curve. Here again, we have to find out, or we have to show the equivalent relation, that is adiabatic relation between point, sorry, Ta Va raised to gamma minus 1, where T and V, Ta and Va are the adiabatic, or here we can say that this Ta Va raised to gamma minus 1 gives the adiabatic relation between temperature and volume at point A. Now at point B, Tb Vb raised to gamma minus 1 is the adiabatic relation at point, adiabatic relation between temperature and volume at point A, B. So from this equation we can write Ta is equal to Vb upon Va raised to gamma minus 1 into Tb, or simply you can write TA is equal to 1 upon rho C raised to gamma minus 1 into TB. Suppose this is equation 4 and this is equation 5. Okay. Now substitute the value of TD and TA in this equation. TD and TA, we have eta is equal to 1 raised to 1 minus 1 upon gamma in bracket. Value of TD is TB 1 upon rho E raised to gamma minus 1 minus this is TC, this one, and then TB in bracket 1 upon rho C raised to gamma minus 1. This is the value of TD which is taken from this equation, and this is the value of TA which is written from this equation upon TC minus TB. Okay. Now again along BC the pressure remains constant. Along BC the pressure remains constant. Therefore TC upon TB is equal to VC upon VB. Why this? Because along BC the pressure remains constant. Or from this we can write what? TC upon TB is equal to TC upon TB. We can write here VA upon VB into VC upon VA. What we did here? We just multiply and divide by VA. Okay. So here, okay. Now like this, D and A are on the same line, hence volume at D and volume at A is same. Therefore we can write, since VD is equal to VA or VA is equal to VD, both are same, then TC upon TB is equal to what? VA, or we can say that VA upon VB into VB upon VC. This VA upon VB into VC upon okay. What we make the change? This is the same relation. Now here VA, VB as it is, and instead of VA we write here VD, because both the points A and D lies on the same line, and hence volume at D and volume at A is same, and hence instead of VA we can write here VD. Okay. And we already studied that this is nothing but VA upon VB. VA upon VB is nothing but compression ratio. In this here, compression ratio, and VC upon VD is expansion ratio. So instead of this we can write rho C upon rho E, where rho C is the compression ratio and rho E is the expansion ratio. Therefore from this we can write From this we can write Tc is equal to Tb into rho c upon rho e. Simply we take this term towards this side and we have this equation. Now substitute this value of Tc in this equation 4. After substituting the value of Tc from this equation, that is, we can suppose this is equation 7. If we substitute this equation in this equation 4, we have eta is equal to 1 minus 1 upon gamma in another bracket. Tc is nothing but Tb rho c upon rho e bracket raised to gamma minus 1. Sorry, not gamma minus 1. Okay, here also. Okay, gamma minus 1. Then here not gamma minus 1, here was simply 1 upon rho e raised to gamma minus 1. Okay. Now this term as it is, Tb in bracket 1 upon rho c bracket raised to gamma minus 1, and this is the bracket. Again we have to substitute the value of Tc here. Therefore Tb in bracket rho c upon rho e minus Tb. Okay. Take the common Tb. Tb take as a common here also and here, and getting cancelled with each other. Therefore we have only eta is equal to 1 minus 1 upon gamma in bracket here. After rearranging this, we will get 1 upon rho e raised to gamma minus 1. Sorry, only gamma. When we solve this term, we will get this term. And when we solve this, obviously Tb is common, 1 upon rho c raised to gamma. Okay. Then divided by, instead of this we can, when we solve this, 1 upon rho e minus 1 upon rho c. This is equation number, suppose 8, whatever it may be. This equation represent the expression for efficiency of diesel engine. Remember that efficiency of diesel engine depends on or depends upon the expansion and compression ratio. Efficiency of auto engine is depends on compression ratio only, but here efficiency of diesel engine depends upon the expansion and compression ratio both. Okay. In this way we obtain this expression for the efficiency of diesel engine. Okay. Now we are going to compare both the engine, or we are going to make the comparison between diesel engine and auto engine. This is very important because number of questions, objective questions may be asked on this difference or comparative study between diesel engine and auto engine. Diesel engine and auto engine. See here, first point, first comparative point, diesel engine is an internal combustion engine. Internal combustion 4-stroke engine, diesel. We already studied this. diesel engine is an internal combustion 4-stroke engine. Otto engine is also internal combustion 4-stroke engine. Okay. That is, when we compare both the engine, then it is found that both the engines are internal combustion type 4-stroke engine. Okay. In diesel engine, oil is used as a fuel. The fuel used is oil. And in Otto engine, petrol vapor or any combustible gas. Petrol vapor or any combustible gas. Combustible gas is used as a fuel. Then third comparative point, oil is injected separately with pump or nozzle. Oil is injected during working stroke. Oil is injected at the end of compression stroke. Oil is injected inside the cylinder with the help of pump or nozzle in the form of fine spray. But here in Otto engine, petrol vapor and air, that is 98% pure air and 2% petrol vapor, any combustible gas, this mixture is admitted as a charge. Okay. What I say, in diesel engine, oil is injected separately with the help of pump or nozzle. But in Otto engine, the mixture of petrol, vapor and oil are admitted as a mixture simultaneously. Okay. Now next point, point number 4. This is the very important point. Here, heat, that is Q1, is absorbed during isobaric change. Okay. And in Otto engine, heat is absorbed, heat Q1 is absorbed at isochoric change. Okay. See here. At constant volume, and here at constant pressure. So here heat Q1 is absorbed during isobaric process, and in Otto engine heat Q1 is absorbed during isochoric process or isochoric change. Now one more point, point number 5. Heat is rejected here. In both the engine, heat is rejected. Heat Q2 is rejected or transferred to the surrounding isochorically. Q2 is rejected isochorically. That means what? Heat in both the engine, heat is transferred to the surrounding at constant volume. Okay. Now, point number 6 is very important. Here, compression ratio is low because oil is compressed up to 1/8 of its original value. Here, compression ratio is high as air is compressed up to 1/7 of its original value. Okay. Now, next point, point number 7. Here, when temperature of the air mixture is rise up to about 500 degrees Celsius, then spark is produced. That means what? Passing an electric spark. Passing an electric spark causes ignition. But here adiabatic compression, air is so compressed that adiabatic compression becomes large. So adiabatic compression causes ignition. Here passing an electric spark causes an ignition. Here compress the gas much more so that it get ignite. Then next point number 8. There is a here there is a danger of explosion. Danger of explosion. Here there is no danger of explosion. No danger of explosion. Diesel engine, there is no danger of explosion, because here due to spark explosion is reduced. So it is danger of it. Okay. Next point 9. Auto engine is light and portable. Light and portable. Here diesel engine is bulky and heavy, or heavy and bulky. And last point, the efficiency of auto engine is low as compared to efficiency of auto engine. Efficiency of diesel engine is high. Okay. In this way we complete both of the practical heat engine along with the expressions for their efficiency. So we shall stop here. Have a good day. Thank you.